A light from deep space should behave like a mirror, not a lamp. Yet 3I Atlas shines with a compact, sunward glow that fades in a way nature almost never produces. Hubble logged it. Classical models strained. Harvard's ATLAS+ says the evidence points to artificial illumination. If true, this is not a comet putting on a show. It is a system under power. Why is it lit, and who decided it should be? The Hubble paradox, a headlamp in the void. The first deep look at 3I Atlas produced a paradox that sent observers back to their baselines. At a solar distance where interstellar visitors usually register as faint cotton puffs, this object appeared almost 200 times brighter than 2I Borisov at a comparable range. That kind of luminosity would normally imply a huge reflective surface and a broad halo of sunlit dust drifting away from the nucleus. Instead, astronomers saw a compact, forward-facing glow concentrated toward the sun. The light was not flaring out like a classic tail. It was gathering tightly in front, as if a headlamp were shining through a thin veil. Brightness alone can trick the eye, so the team did what planetary scientists always do when geometry feels deceptive. They measured how the intensity falls with distance from the center. For ordinary comets built by reflected sunlight, the drop follows a shallow radial curve that comes from simple scattering. For 3I Atlas, the decline was much steeper, tracking a neat inverse fourth power. That profile is familiar in optics, but not as a signature of passive reflection. It is the fingerprint of a compact source that is illuminating surrounding material from within rather than relying on the sun as the only lamp. At that point, ATLAS and his colleague Eric Cato offered a hypothesis that sounded bold and, at the same time, straightforward. They proposed that 3I Atlas is not merely reflecting sunlight but emitting light of its own, which then scatters off a thin dust sheath near the sunward side. Under that interpretation, the object does not need to be a monstrous 12-kilometer reflector. It could be small, perhaps less than a football field across, and still produce the recorded luminance provided it carries the power to drive a 10-gigawatt optical output. The mathematics tie the apparent brightness, the steep radial falloff, and the tight sunward knot into a single picture. You can dismiss the idea as provocative. You cannot dismiss the fit. The size inference matters because surveys are much more likely to catch modest bodies than giants. If you insist the brightness demands a colossal mirror, you must also accept an unlikely roll of cosmic dice at the exact moment our instruments matured. If you accept a compact emitter, you trade improbability for engineering. You must explain how a small body powers that much light and why it shines in a pattern that behaves like a controlled lamp in a managed fog. That is the fulcrum of the debate. In one direction lies a statistical headache. In the other lies intent. The strongest arguments never rely on a single anomaly, so astronomers began adding constraints. Spectroscopy found weak or absent gas emissions that should accompany a massive dust plume. Early light curves hinted at pulses tied to rotation that would make sense for a set of fixed vents or emitters sweeping the sun once per spin. Meanwhile, the geometry of the glow remained tightly clustered. Each new data point narrowed the natural pathways and made the engineered pathway feel less theatrical. It is not that nature cannot surprise. It is that nature rarely stacks this many surprises in one place. Loeb often uses a simple scale for ambiguous objects. 0 means unquestionably natural, 10 means clearly technological. He places 3I Atlas at 4. That number is not bluster. It is a way of saying that the best fit is no longer the most comfortable fit. If the light is active, there is a power source. If there is a power source, there is an architecture. And if there is an architecture, someone designed it. Science advances by removing unnecessary steps. Here, the steps were added by the data, not by a wish. If the glow isn't reflected sunlight, what kind of engine or intention could be hiding inside that tiny point of light? Natural fixes that fall apart. When a result threatens to change the conversation, the first responsible move is to attempt every natural explanation with rigor. The most obvious rescue idea was a dense, sunlit dust cloud wrapped around a tiny nucleus. A thick grain field can scatter strongly in the forward direction and, if the grains are the right size, can mimic a tight glow. That model fails the chemistry test. To loft that much dust you need vigorous sublimation of volatiles. Strong sublimation leaves spectral fingerprints in water vapor or carbon-bearing gases. Those signatures were not detected at the levels a giant plume would require. The glow is not supported by the gas. The second rescue idea made the nucleus truly enormous. If you want brightness without gas, just make the reflector itself so large that it swamps every other factor. The statistics do not cooperate. Interstellar objects the size of small moons should be phenomenally rare compared with modest chunks. If surveys suddenly hit a jackpot that big, you would expect a lead-up of smaller winners. The discovery pattern for 3I ATLAS does not resemble a slow climb toward a giant. It looks like a spike that appeared exactly when our telescopes were ready to notice. Unlikely does not mean impossible, but science reserves unlikely for moments when all other lines close. A third rescue idea invoked frictional heating. Perhaps the body plowed through a dusty patch thick enough to glow. Interplanetary space at those distances is too sparse for that mechanism to matter. The required density would leave other signatures and would still not produce a neatly centered, forward-facing bulb. A fourth idea reached for exotic compact objects such as primordial black holes that could energize nearby dust. The power output of such encounters in a realistic environment falls many orders of magnitude short of the recorded brightness and would not generate the measured radial profile. It is elegant to imagine, and easy to reject when you put the numbers side by side. Radioactive debris is the last refuge of the natural maximalist. If 3I ATLAS were a fragment of a planet torn from a dying star, loaded with short-lived isotopes, could it shine on its own like a dying ember? In principle, yes. In practice, you would need a piece that is almost pure fuel, that survives ejection, that wanders between stars without dispersing, and that arrives here intact. The chain of low-probability events grows longer than the chain you need to accept if you allow an engineered lamp. When two roads are improbable, the one with fewer improbable turns is the honest favorite. Skeptics will correctly point out that cometary physics is complex, that dust albedo varies, and that small bodies often surprise. Those points should keep everyone cautious. Caution does not erase the central problem. The brightness profile, the compact sunward glow, and the missing gas do not want to live in the same natural house. You can make a floor plan that fits one or two. You do not get all three without adding rooms that should not exist. At this stage, good teams do not stop. They ask what measurement would force a decision. That is where the story goes next. Multiple instruments will test whether the light behaves like a lamp or a mirror. Either answer will teach us something fundamental. If the mirror wins, we will rewrite our models of interstellar comets. If the lamp wins, we will rewrite our assumptions about company. Blueprint of a self-lit craft. Imagine a small core wrapped in an engineered microenvironment. Inside the core sits a power-dense emitter. Outside the core floats a thin shell of grains whose sizes are tuned to scatter visible light very efficiently. Turn on the lamp and the grains flare, producing a tight glow that leans toward the sun as photon pressure pushes the envelope slightly off-center. Turn off the lamp and the glow collapses. If the system spins, the brightness rises and falls with the orientation of fixed emitters, creating a periodic light curve. That is the picture Loeb and Kato sketch. It does not require magical materials. It requires intention, a power source, and a reason to shine. A 10 gigawatt optical output raises eyebrows, yet it is within reach for a civilization able to field compact nuclear systems or to store energy at high density. 10 reactors worth of light sounds extravagant only because we compare it to our current spacecraft. It is a fraction of the energy Earth intercepts from the Sun each second. It is the kind of budget you allocate when the science return depends on being seen or when guidance depends on reading your own scattered light with sensitive detectors that feed a navigation loop. The dust shell could be replenished slowly by controlled venting. The spectrum could be tailored for maximum scattering efficiency. The device would be simple in function and elegant in design. A self-lit system also explains why the coma does not behave like a typical atmosphere. Classical comae are driven by gas that drags dust outward, producing the chemistry and dynamics we expect. Here the light itself is doing most of the work in the visible band. The grains are not passengers in a gas wind. They are purposeful reflectors in a managed field. Observers reported a hint of nickel without iron in the tail, a composition that naturally appears in high-temperature alloys and advanced radiators. More data are needed before anyone leans on that clue, but it fits an engineered envelope better than an undifferentiated icy body. Every time you propose technology, you must ask what task it serves. Broadcasting is one answer. Optical signaling can carry information across the solar system without radio congestion and can look natural to anyone who is not paying close attention. Navigation is another answer. A craft can illuminate its own environment and measure backscatter to maintain a precise state vector even in complex gravitational fields. Microthrust is a third. Photons impart momentum. A controlled light field inside a tailored sheath could provide tiny attitude corrections without expelling obvious reaction mass. None of these functions requires our languages or our codes. They require light, measurement, and feedback. All three are present in the data.